Where most nations see only emptiness, heat, and endless sand, Israel saw an opportunity to rewrite the laws of survival. In one of the harshest environments on Earth, the country launched a project so ambitious that it stunned engineers, scientists, and governments worldwide. Through sheer determination and advanced engineering, Israel carved more than 7,450 miles of channels across the desert, creating an artificial river system capable of transporting billions of gallons of water from the Mediterranean Sea to sustain an arid nation. And that was only the beginning. Rather than relying solely on existing freshwater sources, Israel pushed even further, using state-of-the-art technology to transform seawater into clean, drinkable water inside massive desalination plants. A process that sounds almost impossible until you see how it actually works. But before we begin, don't forget to like the video and subscribe to our channel. For decades, the Negev desert in southern Israel was virtually lifeless. Its soil was dry and fractured, cultivation was nearly impossible, and summer temperatures routinely climbed above 110 degrees Fahrenheit. Rainfall arrived for only a few weeks each year, while underground aquifers slowly vanished with every passing generation. Agriculture, the backbone of this young nation, stood on the brink of collapse, forcing many families to depend on water trucked in from distant regions. Just a short distance away, however, lay a striking contradiction: the Mediterranean sea, vast, relentless, and overflowing with salt water. That contrast ignited Israel's boldest vision yet, pulling the sea inland, deep into the very heart of the desert. Approved in 2000, the Desert Water Project carried an investment of nearly $3 billion. With that level of commitment and long-term vision, Israel didn't just create water, it challenged the desert itself, forcing rivers to flow where none had ever existed. Before a single drop could move inland, engineers first had to turn hostile terrain into a workable construction zone. Using high-resolution satellite imagery, ground-penetrating radar, and thousands of wind pattern measurements, teams mapped shifting dunes and identified stable corridors for construction. Survey crews lived for months inside the Negev, drilling hundreds of boreholes, some deeper than 100 feet, to analyze the geological layers hidden beneath the sand. Every route marker was positioned by hand and logged with inch-level precision. Canal alignments were meticulously planned to avoid wind corridors, where a single sandstorm could bury an entire worksite overnight. Hundreds of bulldozers reshaped the landscape, cutting down massive dunes and redistributing sand to stabilize lower areas. The objective was to create a perfectly balanced surface strong enough to support heavy machinery without the risk of collapse. Each segment was scraped, leveled, and verified under strict supervision, with surveyors constantly checking elevations and slopes across miles of open desert. Conveyor systems removed excess sand, while compactors carefully pressed the surface layer, forming a solid and stable foundation capable of supporting one of the most audacious water projects ever attempted. After the bulldozers leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser, more cohesive layer. Using long sprinkler arms and underground piping, they sprayed controlled amounts of groundwater over the site, allowing moisture to penetrate several inches deep. When the sand reached the ideal moisture level, heavy rollers moved in, compressing the surface to eliminate air pockets and lock the particles in place. The constant rumble of steel drums echoed through the desert as each pass transformed loose sand into a solid, uniform foundation. Once the surface dried under the desert sun, it became strong enough to support cranes, concrete mixers, and supply trucks. A solid foundation built using nothing but sand and water. With the base complete, hundreds of excavators and massive dump trucks began one of the largest excavation operations ever undertaken in modern Israel. Every day, roughly 77,000 tons of sand and soil were removed from the Negev desert along a construction corridor stretching nearly 250 miles. More than 1,200 engineers, operators, and workers rotated through shifts, facing daytime temperatures that frequently exceeded 115 degrees Fahrenheit. The canal was shaped with a wide U profile, measuring about 150 feet across at the base and averaging 23 feet deep, to allow water to flow naturally without pumps. The longitudinal slope was maintained within a variation of just about 1 inch per 100 feet, in extremely strict tolerance over such a long distance. Survey teams rechecked elevations with laser leveling instruments every 160 feet, ensuring the canal bed remained perfectly aligned. Most of the excavated sand was reused to form the side embankments, creating levees between 10 and 16 feet high. In elevated terrain, bulldozers cut the soil in successive stages, while in lower areas, trucks hauled and stabilized fill material until the desired elevation was reached. In zones with weak soil, engineers drilled sand piles, roughly 16 inches in diameter to depths of 20 to 26 feet, or mixed cement and clay to reinforce the base and prevent settlement. The worksite stretched for hundreds of miles, dotted with concrete batching plants, mechanical workshops, and engineer camps. Under the blazing sun and constant dust, long caravans of trucks and machinery moved non-stop, like a mechanical river carving the path of a real river through the heart of the Negev desert. This excavation phase lasted months. In the Negev desert, the challenge wasn't just the heat and dryness, but the sand's own thirst, capable of absorbing any exposed water within hours if the canal bed wasn't properly sealed. That's why the lining phase became one of the most critical stages of the entire project. First, the bottom and sides of the canal were moistened and leveled with a layer of fine sand about 2 inches thick. Next, concrete panels 4 to 5 inches thick were cast in sections approximately 16 feet long by 10 feet wide, separated by expansion joints. These joints were filled with heated bituminous sealant to prevent seepage and allow for thermal expansion. In areas with unstable subsoil, an additional HDPE geomembrane layer was installed beneath the concrete, anchored with steel fasteners and covered by a protective sand layer. In total, more than 220 miles of canal were lined with concrete, making it one of the largest waterproofing systems ever built in the Middle East. Along the embankments, engineers planted vetiver grass and desert acacias to stabilize the slopes and minimize sand movement. Seen from above, the canal looks like a shimmering silver ribbon cutting through a golden cyan artery of concrete ready to carry its first life-giving water across the desert. A canal of this scale cannot be just a trench for water. It requires hundreds of auxiliary structures to ensure transport, flood control, and proper flow regulation. At the system's intake, engineers built control structures where water is diverted into the canal through massive steel gates. Along the main route, hundreds of engineering components were installed, including reinforced concrete bridges, spillways, siphons, drainage culverts, and aqueducts that carry water over natural channels. Whenever the canal crosses a road or railway, a new bridge is built to maintain traffic flow. In sections that cross natural waterways, transverse drainage structures large conduits, allow the natural flow to pass beneath the artificial canal. In addition, distribution gates are positioned every 6 to 9 miles to control the delivery of water to secondary branches. Everything must operate in perfect harmony, because a single failure, whether in a gate or an aqueduct, could deprive hundreds of acres of farmland of their water supply. After more than 15 years of construction, the entire canal finally entered the water testing phase. Engineers gradually opened the gates, allowing water to flow through sections while slowly increasing the discharge. Along the route, technical teams inspected every point, measuring pressures, checking for leaks, monitoring embankments, and recording any ground movement. Each deviation was corrected before full system opening. When the first stream of water ran through the canal's dry, cracked bed, the surrounding regions erupted in celebration. Residents called it the day the desert came back to life. Wherever the water arrived, applause followed. It wasn't just a flow of water, it was a flow of hope. The realization of a dream. Generations of farmers had waited their entire lives for the moment when real water finally ran across their land. The Mediterranean's water now flows through the artificial river, cutting across the desert. But it still cannot reach people directly, because it remains saltwater, and in the desert, salt can be just as dangerous as drought. Before becoming a source of life for millions, it must pass through an intelligent desalination system, a chain of advanced technologies stretching from the coast to the interior. Here, seawater undergoes multiple stages: mechanical filtration, sand settling, oil separation, followed by nanofiltration, and reverse osmosis, where every salt molecule is removed, leaving only pure, drinkable water. Digital sensors constantly monitor salinity, pressure, and flow rate, automatically adjusting the process to maintain the highest level of purity. Only after passing through all these layers of control does the water enter the main canal, beginning its hundreds of miles journey across the Negev desert. It is no longer seawater, but a true lifeline for an entire nation built on hope and resilience. The pre-treatment stage may have already captured larger debris and sediments, but seawater still carries countless fine particles and microscopic microorganisms. To prevent them from clogging the heart of the next technology, a fine filtration phase is introduced. Inside massive filtration tanks, black hollow fiber membranes act as ultrafine barriers, blocking algae, bacteria, and even the smallest remaining particles. The initial filtration stages are only the beginning. The decisive phase takes place inside the reverse osmosis system. Under extreme pressure, seawater is forced through semi-permeable membranes whose pores are hundreds of times smaller than a human hair. This invisible barrier allows only pure HO molecules to pass through, while salts, heavy metals, and chemical compounds are retained. High-pressure pumps generate dozens of bars of compression, transforming the salty, cloudy mixture into an almost pure stream. However, when it exits the reverse osmosis modules, the water is so pure it becomes almost empty, and this absence must be corrected. Precision dosing systems add small amounts of calcium and magnesium to rebalance the pH and restore a clean, natural taste. Next comes disinfection. Ultraviolet light, or ozone, eliminates any remaining microorganisms. while a small amount of chlorine ensures safety throughout the pipelines. Every parameter is monitored in real time, and laboratory samples are continuously analyzed. Only when all standards are met is the water pumped from reservoirs into the distribution network, flowing through miles of underground pipes to homes, hospitals, and factories. It is a complete cycle in which ocean salt is transformed into safe drinking water, testament to the remarkable power of modern technology. When the first flow of water crossed the Negev desert, everything began to change, not just the landscape, but the lives of the people. Lands that once cracked under the scorching sun began to come back to life. Farmers who had left because of drought returned, setting up tents, driving stakes, and plowing the first fields of their lives amid sand and rock. Water from the main canal was distributed through a network of secondary channels, pressurized pipelines, and drip irrigation systems that delivered it directly to each plant. A technology invented by Israel itself to save every drop of water as if it were gold. The project began in 1953 and took more than 11 years to complete, costing around 420 million Israeli liras, equivalent to hundreds of millions of dollars at the time. When it became operational, the system was capable of transporting up to about 19 million gallons of water per hour, carrying fresh water from the north to the south of the country. Reaching the Negev, as a result, regions once considered hopeless were transformed into thriving agricultural zones. In the early years, tens of thousands of acres turned green, where there had once been only dust and sun. Orange groves, vineyards, wheat fields, vegetable gardens, and rows of fruit-laden date palms emerged. Seen from satellites, a long green belt snakes through the Golden Desert, the green artery of Israel, the artificial lifeline connecting the north and south of the country. The transformation went beyond the fields. Villages were rebuilt, children gained access to schools, and high-tech farms rose from the sand. And so, you've now learned the full story of how Israelis removed billions of tons of sand from the desert to create one of the longest artificial rivers in the world. Were you impressed by this technology capable of turning seawater into fresh water? If so, tell me. Thank you for staying with me through this video, and remember to follow our upcoming content.